is right. Hopefully. I can't see the pace, so hopefully I'm assuming. Okay, so let's just. Why is the census too less today?
Today is Friday, that's why maybe.
Yeah, everyone is taking rest, and it's an online class, so leave it. Next week you'll be having your mid-sem. Next to next week, right?
Yes.
Okay, so Rajni, you were saying something.
Yes, yeah, actually, saying like we can try the nth term is like tending to zero or not. Like it's not tending to zero, we can say it's not converging.
Yeah, nth term is not going to zero. You can prove. Like there are two methods. Either by comparison test or you can prove that nth term is not converging to zero. Yes, that's fine completely. Okay, so let's just start with the today's thing. So today so there's just one more result which is left as a properties of continuous function, and then we'll be finished with the first two sections of continuity. And today I'll cover all the back exercise questions of your uh, section 2 of continuity, like applications of intermediate value theorem. So whatever theorems we have covered till now, today we'll apply in the questions. And then questions related to your basic concepts of continuity, that we'll do in the next class, first section, back exercise questions. So till what sir has covered the course, if anyone wants to share who attended classes, till what portion he has covered the course, what is the last topic that has been done.
I got to know like it was intermediate value theorem on one day when I missed the class, the last class.
Okay, so yeah, so that means we are moving ahead of him. So we have seen some of, so let's start with the recalling part first. Also, I forgot to like send you the notes, so maybe probably I'll send both of these notes together today or by tomorrow. So let's start recalling it. We start with the continuous function. We did epsilon delta definition, and then we proved that it's equivalent to sequential criterion. And then we did algebra of continuous function, which says that if f and g are continuous function, then f plus g, f by g, where g of x naught should be non-zero, and your fg, and then maximum of f and g, all of them are continuous. And then we prove that composition of two continuous function is continuous if f is continuous at x naught and g is continuous at f of x naught. So this implies g of f is continuous at x naught. And then And then we started with properties of continuous function. So in the case of properties of continuous function, the first property that we did was if f is continuous on closed and bounded interval, then f is bounded, and f also attains maximum as well as minimum. Fine. So if f is a continuous function on closed and bounded interval, then f is a bounded function, and it also attains its maximum value as well as minimum value. Attains means that you have a pre-image for the maximum value and you have a pre-image for minimum value. And then we did intermediate value theorem in the last class, that if f is continuous function
when we are writing the interval, do we not need to write a comma in between?
Oh yeah, that's right. You understood what it means, right? So if f is continuous function on an interval on AB, so if f is a continuous function on closed and bounded interval such that or you can say if f is continuous function on closed and bounded interval, and if there exists a point y, then there exists x naught in AB such that f of x naught is y. That means f attains each and every value lying between f of a and f of b. Yes. Jishnu, you want to say something?
No.
Oh, so your mic was on. Okay, so this is intermediate value property, that if you have any value lying between your range set, that means it should attain y. And one more result will be presented by Nahida today, that image of continuous function is either an interval or a single point on intervals. And then we did one of the application of this intermediate value theorem, that if f is a continuous function from 0 1 to 0 1, then f has a fixed point. So by the meaning of fixed point, that means there exists x naught belongs to 0 1 such that f of x naught is x naught. That means it will intersect your y equal to x axis. And now the next thing that we will do here is another application. We'll see another application of your intermediate value theorem, which says that, so let's start with today's topic. And then one of the application of intermediate value theorem is, if you have any positive number and your m belongs to natural numbers, then y has positive mth root. What do you mean by positive mth root? Positive mth root means y will be equal to some power of m. Any positive number will become positive mth root. That means if you have that means if you have a positive number, it will that means if you have any positive number, it will be of this form. There should exist some x such that y is equal to x raised to power n. Okay, so that it will become mth root of x. So anyone is having any idea how to proceed? It's just a one-line proof of intermediate value theorem. You need to construct a continuous function, and then you have to tell me f of a and f of b, and then by intermediate value theorem, you will have that the number should have three image. So what should be your continuous function here? F is a function from continuous function on closed and bounded interval. What should be your continuous function? See, you want to prove that y should be equal to x raised to power m. That means your function should be equal to x raised to power m, right? It's a continuous function because it's a polynomial function. And then I'll prove that for every y, what do you have? Like if for this y, what do you have? That there exists some positive number such that y will be less than b raised to power m. How can I write this thing? That there exists some positive number such that y will always be less than or equal to b raised to power m. That means it will be bounded by some element, some image element. How can I prove this thing? So I'll break this proof in two cases. First case is if y is less than equal to 1. It's a positive number, right? So if y is lying between 0 to 1, what should be my b?
One.
What should be the candidate for b? Yes. So if y is less than 1, y is less than equal to 1 raised to power m, right? So then take b equal to 1. And if y is greater than 1, then what should be the candidate for b? Y is a fixed real number. You are not varying y. Y is a fixed positive real number. So if this number is strictly greater than 1, what should be the candidate for b? Take b as y itself, right? It's a positive real number, so it will be less than equal to its mth power, right? So take b as y itself. Y is fixed, y is not varying. That's why we can choose our b to be y raised to power m itself. So what does that mean? That means that for every positive real number, there always exists a b positive number such that y is less than equal to b raised to power m. That means there always exists b greater than 0 such that y is less than equal to f of b. Right? D raised to power m means f of d. And what is f of 0? It's 0, right? Y is positive. So this thing holds. Is it correct? So did you have the setup now for intermediate value theorem? Y is lying between f of 0 and f of b. Now what? Apply intermediate value theorem. You'll have there exists some x naught belongs to what interval? Belongs to
Interval of 0, b.
0, b, such that f of x naught is y, right? That means x naught raised to power m is y. So y becomes the mth root of x naught. Fine. X is the mth root of y. Fine. That means if you have any positive number, that is always the mth root of some. That will always become mth root of some number, some positive number. So suppose you have 2, it is the mth root of which number?
4.
Mth root, not second root. Mth root. Mth root of which number? Two raised to power m, right? If you have, this becomes mth root of 2 raised to power m, right? Your 2. Right? What x raised to power m should be 2, right? So x is this thing. Now, let's see the partial converse of your intermediate value theorem. You have seen your intermediate value theorem. Let's see how does partial converse look like. Is the converse true? Anyone wants to comment? Is the converse true? That if intermediate value theorem says that if f is a continuous function on closed and bounded interval, then it attains every value lying between f of a and f of b. So if f, so the converse statement would be if f of a, if f is just a function, okay, closed and bounded interval, if f is just a function from ab to r, and if y is lying between f of a and f of b, then there exists x naught such that f of x naught is y. Does this imply this thing is true? that every y lying between f of a and f of b implies it has a pre-image. So does this imply that f is continuous? Is this thing true? Partial converse.
Yes, it must be true, I think.
Why?
Because we are leaving no gaps, right? Every image value is attained.
So what? If every image value is attained, why it has to be a continuous function? You can still have discontinuity. See, this is your A, this is your B, and suppose this is your f of A, and this is your f of B, right? Now, any y which lies between f of A and f of B, you are assuming its pre-image here. That means f passes through each and every value through here. F passes through each and every value. But why it should pass continuously? Why it should pass continuously? See, this can also be the function, right? I'll come up here and then break this function, and then I'll start with here and then reach here. Still it is assuming each and every value, right? Between f of A and f of B. Is it correct or not? Each and every value, each and every point that you pick here, suppose you pick this point, it has a pre-image. Suppose you pick this point, it has a pre-image, right? But it's not a continuous function. There's a break in between. So did you understand? Suppose I'll construct such a function. Say x if a is less than x is less than a plus b by 2. Or I'll be more precise and say here to half this function looks like x, and then half to 1 it looks like 2x. Then is this a continuous function? Is this a continuous function? It's a function from 0, 1 to r, right? Well-defined function. Tell me, it's a well-defined function, right? Is it continuous?
No, ma'am. The left hand limit
It's
and the right hand limit.
Is it continuous, Nikita, or discontinuous?
For 1 by 2, the left hand
Yeah,
and the
what
right
happens
hand.
at 1 by 2? Limit does not match, right?
Yes.
So your left hand limit is half, but your right hand limit is 1, right? Which is equal to the value of the function. But limit does not exist even. Continuity is like much ahead. Limit does not exist. But it is assuming every value from what is your f of a? F of 0 is 0 and your f of 1 is 2. So between 0 to 2 it is attaining each and every value, right? No, 1 second. Sum of the values is so between 0. This is your function till here and there is a gap, and now you are defining half 2. As this. Oh no, so it's leaving some of the values between 0 1. So let me just manipulate it in some other way. Shoot. Yeah, so let me write in this way. Suppose this is your A, this is your B, and you take your function to be this. Yes. Now it is not leaving any value like this. So this is your f of A, f of B. Fine. Or I'll construct it so that I can write the function also. How about this function? Your f of x, suppose this is minus 1, 1. Your f of x is x square if your x is -1 to half. Suppose this is your half. And now from half to 1, this function is 2x square. Or uh, you can say just shift it this thing by 1. X square plus 1. Now what about this thing? Is this function continuous at half? This function is not continuous, right? Limit, left hand limit is not equal to right hand limit. So f is discontinuous at half. But now it is assuming each and every value lying between your f of -1 is 1, and if your f of 1 is 2. So it is assuming each and every value lying between 1 and 2. Right? This is your 1. And suppose this is your 2. Or just make it in this way so that it assumes each and every value. Like define it accordingly so that it assumes each and every value. Just extend your this thing left side. Take -2. So now -2 is 4, and it is assuming each and every value between 2 and 4. So is this clear? Why the converse does not hold for intermediate value theorem? Are there any doubts? Is the function clear? You don't need to define the function, but at least just look at the graph. It can assume each and every value lying between here and here, but still this function can be discontinuous. It is not necessary that the function has to be continuous. So the converse does not hold, but partial converse hold. That if we put more restrictions on it, that will hold. Is the concept clear, Atul, Nikita?
Yes, ma'am.
Atul,
Yes, it's clear.
did you get the answer?
Yes.
It can attain each and every value lying between f of a and f of b, but still it can be a discontinuous function. Because you can create your function looks very bad so that it can attain each and every value, but it is not necessary that every function is continuous. Fine? So this does not hold. The converse is not true. So that's why we'll prove the partial converse. So let's see the partial converse. The partial converse says that here you require one more condition to prove the converse part, which is your function has to be strictly increasing or strictly decreasing. So let g be strictly increasing function on an interval I is AB, such that image is an interval. Interval means it assumes each and every value. Image is an interval on I. Fine, Gj is an interval, not Gi. It should be Gi. Image is an interval this should be J. Then F is G is continuous on J. Is the statement clear? Now you put three conditions. That closed and bounded interval, your J, and then it assumes each and every value, which is image is an interval. That means any value lying between the 2 points is also attained. And then strictly increasing. So if you are putting three things together, then you can say that it's a continuous function. Here it is not continuous because I have constructed not strictly increasing or decreasing function. I have violated that property. But if your function is strictly increasing or strictly decreasing, then it has to be continuous. So how does the proof should look like? So you have to prove the continuity on J. Continuity on J. So let's start with any point. Let x0 belongs to J and assume that it's not an endpoint, because if it is an endpoint, then the theory is not interesting. Then you can manage if it is an endpoint, because you just have to check one side limit at the endpoint. Main thing is to check what happens in the middle. So assume that x0 is not an endpoint. Of J. So if x0 is not an endpoint, then image is also not an endpoint. Why? Anyone wants to answer why? If x0 is not an endpoint, image is also not an endpoint on I. Why? How does your function look like? It's a strictly increasing function, right? It's a strictly increasing function. So if this is not an endpoint, so the image of this is also not an endpoint, right? Endpoint will be this. So if x0 is not an endpoint, image will also not be an endpoint, because the endpoint is the point where your function ends. The image is also not an endpoint. Why? Because it's a strictly increasing function. If something increases on the x-axis, your image also increases. That is what the definition of increasing function. So which implies if it is not an end point, that means you can create an interval, right, around g of x naught, such an interval which lies completely on I. Because it's not an end point, you can create a very small neighborhood around it. So there exists some epsilon naught such that g of x naught minus epsilon naught and g of x naught plus epsilon naught is contained in I. Here, this is your I image set, and this is your J. Fine. Is this part clear? How I created this neighborhood? And now you start proving the continuity. Let epsilon greater than 0 be given. Fine. Epsilon greater than 0 be given. Since your function is assuming each and every value, it's an interval, each and every intermediate value. So it will assume this and it will assume this also. Right? It will attain this thing and this thing. That means there exists x1, x2 in J. That means these numbers should have pre-images, right? These numbers should have pre-images on J. Because intermediate value property holds here. Such that g of x1 is and g of x2 is so till now everything is clear or not? I just choose a point at which I have to check my continuity and I assume that it's not an end point. So its image should also not be an end point. That means I can create a neighborhood which completely lies in the interval. That's why it has pre-images. It completely lies in the interval. That's why by intermediate value property, it should have pre-images. Here intermediate value property holds and I am proving that it's a continuous function. Fine. So now what does you have? Your x1, this is your x1, this is your x2. So your x, since it's a strictly increasing function, so your x1 is less than x0 is less than x2, right? Or if you start with, if you take any point lying between x1 and x2, since it is an strictly increasing function, g of x1 should be less than g of x should be less than g of x2, right? Because g is increasing, strictly increasing function. Now what do you have? What is g of x1? G of x0 minus epsilon is less than g of x is less than g of x0 plus epsilon. So here I am choosing my let epsilon greater than 0 be given such that this epsilon is less than your original one. It is lying here and here. Fine. So this is the definition of continuity. G of x minus g of x0 mod is less than epsilon. But now you have to find your delta. What should be your delta? What's your delta here? I have made an assumption that x is lying between x1 and x2. So my delta should look like minimum of x2 minus x0 and x0 minus x1. So whenever my x minus x0 is less than this delta, right? Whatever is the minimum, then you have this condition, right? If the minimum is x2 minus x0, so then you have this condition which clearly shows that this is less than x2, your x. And if you have the other way side, then also it will hold. So whenever this is less than delta, this implies is this proof? I know it's a completely tricky proof, but all the proofs in continuity chapter is like this. I can't do anything.
Could you please explain?
Yes? Okay, I'll explain. So,
Can you please explain the delta part again?
see, I want that my x should lie between x1 and x2. Then my g of x minus g of x0 will be less than epsilon. So how do I get this part? I have to manipulate my delta in such a way that whenever x minus x0 is less than delta, I should get, whenever x minus x0 is less than delta, I should get x1, x lies between this thing, and now this proof will imply that g of x minus g of x0 is less than epsilon. That's why I've chosen my delta to be this, so that this equation holds. Fine. If x minus x0 is less than delta, then your x is lying between x1 and x2. Choose any value, whether this or this. It will hold. And then when this thing will hold, here is the proof how it is less than epsilon.
Okay, ma'am.
Nikita, is it okay, or should I explain you again?
Okay.
See, you have your x0, and then you want to prove the continuity at x0 to make use of intermediate value property, increasing function, and closed and bounded interval. So what did you do? You assume that it's not an endpoint, therefore there exists a neighborhood which completely lies in the interval, and then you started with your definition of continuity. Let epsilon greater than 0 be given, such that you want to prove it for small epsilons, right, which are tending to 0. The distance should become small. So that's why I put one more condition. And now, since it has intermediate value property, therefore there exist 2 points such that this value is obtained and this value is obtained. And now whenever your x is lying between x1 and x2, I apply that the increasing function. So this value is less than epsilon, and then I manipulated my delta in such a way that I get the definition of continuity. This is the whole proof. I know it's a very tricky proof, but I guess the questions will not be that tricky. The only thing is just to understand these theorems, because all these theorems has a lot of application in solving problems. So now one more theorem has been added to your list. First one was bounded. If f is continuous function on closed and bounded interval, it is bounded. And then next is it attains its maximum as well as minimum. Another is intermediate value property. Third one is fixed point, that if f is lying between 0, 1 to 0, 1, it has a fixed point. And now fourth is partial intermediate value theorem, partial converse of intermediate value theorem. That if partial converse of intermediate value theorem, which says that if f is increasing function on an interval j, then on an increasing function and it attains each and every value between, and f of j is an interval. That means it has intermediate value property. Then f is continuous function. Fine. So one more thing has been added to your list now. All these theorem combines and they will help you to solve more and more problems, whether on the exams or on the entrance level. All the questions usually come from these four theorems. It's like these four theorems are the building blocks for continuous function. And the most important one is the first and second. These are the most important ones. So let's just see some of the applications in exercises. Let's just solve some of the exercise problems and see where these questions, where we have to apply these theorems. So one of the exercises 18. So today I'll finish with the 18 section, 18 back exercise of the 18 section. I'll try to finish. Let's see whether I can or not. So the problem 18.4 says that if there exists a sequence xn belongs to S, let S is a subset of R. So if there exists a sequence in S such that xn converges to x0, but this point does not belongs to your set, you have to prove that there exists an unbounded function on S. Fine. You have to prove that your function is unbounded. Like you have to find a function which is an unbounded function. That means what property you have violated here? If f is a continuous function on closed and bounded interval, then it is bounded, right? Your theorem says that if f is continuous function on closed and bounded interval, then f is bounded. But now this exercise tells you that you can construct an unbounded function on S. That means what goes wrong here? You can construct an unbounded continuous function. That means continuity is there. So which condition we have violated? That's why the function becomes unbounded. You have a counter example. So which property you have violated here?
IVT.
What?
IVT.
No, I didn't understand. Your voice is too low. Rajni?
Yes, ma'am. IVT. Like intermediate value theorem.
No, intermediate value theorem we are not applying here. We are saying if we apply this theorem is not true for this exercise. Why? Why this theorem is not true for this exercise? How you can construct an unbounded continuous function? Because this theorem says that if f is continuous on closed and bounded interval, it has to be bounded. So how I can why they are asking for constructing an unbounded continuous function on the set S? What goes wrong here? Why I cannot apply this theorem on continuous function? Just try to recall the remarks that I created after proving this theorem. Just continuity is not enough to apply this theorem. More condition is required. What is that condition? Just continuity of the function is not enough.
Is it that it has to attain the maximum and minimum value?
That is the application of this. This will imply f is attains maximum and minimum. I'm trying to say why you cannot apply this theorem. How can you have a counter example if this theorem is true?
X naught is not S.
Yes?
X naught is not in S.
X
X naught
naught
does not belong.
X naught? Yes, Divisha?
X naught does not belong S naught.
So if x naught does not belongs to S, what happens? Like here you don't want any point to be in the set, right? What goes wrong here if x naught does not belongs to S?
It's not understood.
Yes? See, here you are just given S to be a subset of R. Whether it's a closed and bounded set or not, you don't know, right? Whether it's a closed and bounded interval, you don't know the condition, right? You can apply this theorem if f is continuous function on closed and bounded interval. But here, there is no condition given on the S, whether it's closed and bounded. S can be of this form, right? S can be of this form 0, 1, union 2, 3, right? It's a bounded function, but it's not closed, right? It's not a closed interval. And even just this thing 0, 1. So don't try to invoke such theorems on such type of intervals. You can apply the theorem if your interval is closed as well as bounded, right? If it is a closed interval. Is the meaning clear? How we are having a counter example why this theorem is not true in this case, in this exercise? Is the meaning clear? Atul, is the meaning clear?
Yes, it's clear.
Why you have an unbounded continuous function here? Because at that time when I was proving this theorem, at that time also I gave you a lot of example where you violate this property, then you can have an unbounded function, right? If you want to create a function from 0 1 to r, just take this function. It's an unbounded function, unbounded continuous function. Why? Because your interval is not closed, it's an open interval. So how you can construct an unbounded function? What function should I define here? Define f is a function from s to r such that f of s x should be any continuous unbounded function that you can create with the given information. Any suggestions? How I can create an unbounded continuous function with the help of this sequence and this x naught? See, this is your point x naught, right? And you have a sequence which converges to x naught, but its functional value, like it converges to x naught, but your set does not contain this point. Your set is open from this side. So what function should I draw here so that it becomes unbounded?
Maybe something like a tan function which tends to infinity, something similar to that.
Yes, the idea is that just take something which has a branch here, like which becomes, like this line becomes the infinity branch, like it tends to this line. Fine. Such type of function become unbounded and it is continuous and it is also well defined. So the function should look like x minus x naught mod. Right? Is it an unbounded function? First of all, it is well defined, right? Because x naught does not belongs to your domain. If x naught does not belongs to your domain, you can put it x minus x naught in the denominator. It's non-zero. X minus x naught is non-zero, right? Non-zero quantity. Because it is not in the domain. This point. So it's a continuous function. And how will you prove the continuity of this function? What's your argument for the continuity of this function? Apply theorems. Apply the theorems that you have done for continuous function. X minus x naught is a continuous function. Polynomial function. So mod of this should be continuous function. We have proved that the modulus of continuous function is continuous. And then apply algebra of limits. Right? Function is non-zero at x naught. So this is continuous function by algebra of continuous function. So continuity is proved. F is continuous function. Now what about unboundedness? Is the function unbounded or not? How can you prove that the function is unbounded? Why the function is unbounded? At least respond something. Why the function is unbounded? C. Make use of the thing that xn converges to x naught. So suppose if I assume that function is bounded, okay, I'll prove by the method of contradiction. Suppose f is bounded. What does that mean? F of x mod is less than m for some positive number, right? And then that means f x minus x naught mod is less than m for all elements of S, for all elements in S. What does that mean? X minus x naught mod is greater than 1 upon m. Now at least you got the contradiction. This equation holds for all the points of S, but your sequence converges to x naught. What does that mean? So if you choose your epsilon to be 1 by m, there exists some k such that xn minus x naught mod should be less than 1 by m, right? But this equation says that it should be greater than 1 by m for all the points of S, and sequence are the points of S, right? So you are getting two opposite statements, which is a contradiction to one. Is it clear why this function is unbounded? Why the function is unbounded here? Please respond something. How do I
Yes,
get
ma'am.
to know? That's why I really don't like these online classes, because I can't see the faces whether you are there or not, whether you are understanding the proof or not. Fine. Is it clear that it's an unbounded function as well as continuous on S? So this is your problem number 18.4, and it's a very nice problem because it helps you to have a better understanding of this theorem, that you cannot apply this theorem everywhere. You should be very careful while applying this theorem. You need continuity as well as closed and boundedness of the interval. Don't invoke theorems anywhere. Be very careful. What are the hypotheses? Let's go to 18.5. I guess that would be easier problem for you. So A part says that so just one answer. Have you guys even started studying continuous functions, or are you still on the series? That's why all these things are not making sense to you.
Until today, we're still on series.
Atul, have you started studying continuous functions? Yes, please.
I've just understood the theorems. I've just understood the theorems, but their applications are not clear yet.
Start studying these properties of continuous function. Otherwise, I'll be moving ahead and you are lacking behind. Start at least understand these four theorems, because these four theorems are really helpful. Like these are the most powerful tools of continuous function. And the techniques of the proof is also really important, because those techniques will be required if you will take maths ahead. Those techniques will always be required in case of topology. You have to go through all such techniques, because you are just dealing with the real line now. You should be very careful while constructing these sequences and having then arguments, constructing supremum, infimum. You should be very comfortable with real analysis if you are planning to take maths ahead. So you should understand this continuous chapter every time you'll encounter with the continuous functions. So let f and g be continuous functions on AB. Now everything is given to you, continuous as well as closed and bounded interval, such that f of A is greater than equal to g of A and f of B is less than equal to g of B. Now you want to prove that there exists a point in AB such that g of x naught is equal to f of x naught. That means, so at some point these two functions will be equal, at least for one point. How to go for the proof of this thing? Any idea? You just have to apply the theorems that we did today. That like the theorems that we, one of these theorems. Either intermediate value property or this maximum minimum, or the third one. Fourth will not be applicable. Or you have fixed point theorem. So you have two continuous function on closed and bounded interval. Now what? You want to prove that at some point these will be equal. What should I do? What should I write now? Any suggestions? See, this exercise has the same proof that we did in one of the theorems. Same technique will be applicable. Okay, the hint is you have to
Will we
apply.
use intermediate value theorem?
Yes, but how? How we have to apply intermediate? Like we have to reach the setup, right? Continuous function, closed and bounded interval, and then you need a point, line between 2 points. Then it will have a pre-image. So what should be my point? If I define a new function AB to R such that h of x is gx minus fx. Same proof we did for fixed point, right? When we need to prove that f has a fixed point, we defined this new function, right? F of x minus x, and then we proved that at some point 0 is attained. Same technique will be applicable here. It's a continuous function on closed and bounded interval, And now, what is h of a? G of a minus f of b. And sorry, f of a. And g of b minus f of b. Now what? What is g of a minus f of a? Now at least speak up the proof. It's already there. G of a minus f of a is, look at the
Less
conditions.
than 0.
Yeah, so this is less than 0 and this is,
Greater than 0.
so that means 0 is lying between h of a and h of b, right? So if 0 is lying between them, that means by intermediate value property, there exists some x naught in AB such that h of x naught is 0, right? That means now you should be very familiar with constructing such arguments. You have to construct such arguments again and again. Because the problems on continuous function will not be that easy. It's not always proved that it is a continuous function. You have to apply the theorems. Is the proof clear? How we made an application of intermediate value property? Similar proof, similar exercise. Let's see. At least now you should construct the proof. Prove that x equal to cos x for some x in 0 to pi by 2. Same, you have to apply intermediate value property here. How can you prove x equal to cos x for some point? How I can apply intermediate value theorem here?
We can do the exact same thing we did.
What function should I define now?
Same thing, maybe cos x minus x.
Yes, the function that would be cos x minus x. But to apply the theorem, I need closed and bounded interval, right? Right?
Yes.
X should be closed and bounded interval, continuous function on closed and bounded interval. So what is the manipulation that is required here? How does your cos function look like? What's the graph? Right, this is your 0 and this is your pi by 2. Then what? What closed and bounded interval should I take? Just take 0, 1, right? On closed 0, 1 is lying here. So if you get a point between 0 and 1, that means you get a point between 0 and pi by 2, right? If f is a function from 0, 1 to r such that f of x is cos x minus x, continuous function, closed and bounded interval, and what is your f of 0? 1, which is positive. And what is your f of 1? Cos 1 minus 1, right? Which is less than 0. Because the highest value can be at max 1, right? Highest value is at max 1. So that means 0, f of 1 is less than 0 is less than f of 0. So by intermediate value property, there exists some x naught, right, in 0, 1, such that, and it cannot be 0. Why it cannot be 0? Because at 0 you already know the value. At 0 it is 1. It is not 0. So that means the point is lying between 0 and 1. Even open 0, 1. And this is a subset of your 0 pi by 2. Right? So now, if your point belongs to 0, 1, that means it belongs to 0 to pi by 2, right? And you want a point here, 0 to pi by 2. See, all the time your proofs will not be so easy. You have to manipulate somehow. You have to use your brain. It's not like you just have to apply the theorem. You have to construct, like you have to reach the place where you can apply the theorem. You have to construct something. Is it clear now? Okay, so that's all for today. Nahida will present a proof that image of an interval will always be an interval under a continuous function or a singleton point. So she'll present a proof, and in the next class we'll do more questions. We'll complete this section, 18 section. We'll complete the exercise of this section, back exercise, and then hopefully I'll complete your homework, latest homework on continuous functions. I don't know what's the number, homework 5 or 6, but I'll try to complete your homework 5 and 18 section. And then I also spend one more class where I'll collect your doubts and prove back exercise of 17 section. So for the next two classes, we'll not start with the new concept. We'll spend time on the solving more and more exercises for the next 2 classes. Monday and Wednesday. And then let's see whether sir will cover uniform continuity or not for your next midterm. So did he told what he'll cover, what should be the syllabus for your next midterm? Till what?
I believe.
Anyone is attending classes or not?
Yes, ma'am. But actually, the thing is, last time also I asked him about the what would be coming in the midsem. He said like it was a day before. Of course, it was like mistake on my part. But he said I'll check and let you know tomorrow. Like, and tomorrow we had the exam on next day.
Fine. So my guess is these 2 sections will definitely be there, and one more section will be there. But I don't know that which section will be there next section. So that's why I'll not start with the uniform continuity. will focus on these two sections, and when he'll start with the next section, let me know. I'll start with the next section, because the syllabus for the next midterm probably be series, and then limit supremum infimum part, and these two sections from continuous functions, and one more section will be there. Right now I don't know what section will be there.
And the sequences.
Sequence will not be there for the next midterm. Sequence was covered, right, till your first midterm. Sequence. Yeah, Nahida, are you there?
Hello.
Yes.
Okay. So we have to prove that if f is a continuous real valued function on an interval I, then the set f of I equals fx, where x belongs to I is also a single point or an interval. So in the first part we are going to prove.
Just 1 second. Just 1 second. Maybe I'll download it. A single point. So you started with the first thing. So you started with the first case that if the image is a single point, that means it's a constant function. So if it is a constant function, then you really don't have to prove anything. Then you don't have to prove it's a constant function. So the main thing you want to prove that when it is not a constant function, right? So if it is not a constant function, then infimum and infimum will be strictly less than supremum of j. Okay, so infimum will always be strictly less than supremum of j. Then if it is strictly less, that means one of the point is lying between infimum and supremum, right? And what do you have is it's a continuous function on closed and bounded interval. So by intermediate value property, this value should be attained. Okay, so this value should be attained. What did she did? Neither are you there? What you have written? See, maybe I guess I'll just write down the proof. So if your function is a single point, then you really don't have to prove anything, nothing to prove. And if f is not a singleton set, okay, if the image f of I, if the image is not a singleton set, that means 2 points will be there, right? At least 2 points will be there. So if 2 points will be there, it has a supremum as well as infimum. Why? Because f is a continuous function. F is continuous on closed and bounded interval. So if f is continuous function on closed and bounded interval, it has maximum, it has infimum, it will have supremum. So your infimum of f of I will always be less than supremum of f of I. Fine. If the infimum is less than supremum, you want to prove that this thing is an interval. So when does this thing will be an interval? That if you assume any value lying between supremum and infimum, if you assume any value lying between supremum and infimum, it should have a pre-image. So by intermediate value property, you will have that it will have a pre-image. So you are using two of the properties simultaneously. That first thing, every continuous function on closed and bounded interval attains maximum and minimum, and second thing, it will have an intermediate value property. So this was a main crust of this proof. Fine. Is the proof clear, or are there any doubts related to this proof? So the image of an interval will always be an interval under continuous function, or either a single, or it will be a constant function. Fine. So let me stop sharing it. So are there any doubts related to anything?